then, because if I don't record, then I have to re-give this lecture to my basement tomorrow. And that is so much less fun than talking to you all. So welcome back. We have, let's say, just for the folks who are only watching the videos, a reminder, homework on Monday night is due. Let me know if you have any questions as you work your way through that. And I just posted new material for next Tuesday, just a few minutes ago, example 4B that goes with the sort of the second half of this lecture here. And then after that, we're turning a corner and starting to head into multivariate models instead, starting with just regular old regression, but for multiple outcomes at the same time, and then eventually heading into generalized multivariate types of models. And let's see here. We've done discrete. Now we're heading towards continuous. So how about I start this thingy here so we can see what we're all looking at here. So roadmap, where we've been, where we're going, first off. So still in the world of generalized models, which means that we're having regressions, except we're adopting a link function to make sure that our predicted outcomes stay within the boundaries they're supposed to. And we're choosing a different conditional distribution that will better match what the residuals look like than normal. So what we've done so far then is categorical outcomes as they are known more generally. So specific types of categorical would be binary, ordinal, and nominal. If you are in the IRT class, what do you call categorical outcomes? Starts with a P.
Polytomous?
Polytomous, yes. So trying to make connections across disciplines here because there are a lot of words that turn out to mean the same thing. So we did that much. We have multinomial or Bernoulli distributions and then usually some kind of logit, probit, or log-log link for those. We just finished up counts. So counts are still also discrete because they can only have integer values. They are bounded at 0, but they don't have an upper bound. So the link to address that single boundary is a log link. And for the most part, there's others, but I rarely see them mentioned. And then some kind of Poisson or negative binomial. And then there's an extra hurdle here, pun intended, of whether or not you have extra zeros. So that's zero inflated. The idea that we have a separate submodel so that we can predict the logit of being an extra zero, or we just take the outcome and cut it up into 2 and predict whether or not someone has a 0 and then how much of the count if not. So these ideas of zero inflated and hurdle are going to come back in what we're going to talk about today and Tuesday as well, because outcomes that are continuous can also have extra zeros or zeros at all, which some of the continuous distributions don't have. So what we will do about that. So that's where we're headed here. And just as sort of a step back, would you like to guess, would someone like to guess, out of all the stuff that we've covered in this class thus far, how much of it I learned in grad school? Would anyone like to guess as to a percentage or the content? Almost none? That is an excellent guess because that is correct. So when I left grad school, I knew how to run regression models. 10%, I would say maybe a little under, actually. Almost none is probably closer. Let's go with 5%. I knew how to run regression models. I did not know how to do estimate statements. So all of the linear combinations to get the missing mean differences or to get simple slopes out of interaction terms, I learned how to do those things after I started on the tenure track. So I knew almost none of this. All of this material I had to teach myself so that I could teach it to other people. So I say this to make sort of 2 points. We were speaking to a student this morning about some work she was doing, and I was telling her, look, I couldn't have done this work that I just asked you to do either. So that is to say 2 things. This is a lot. Like, I have chosen to make this course more of a survey course in the sense that we spend like a day or a week on a set of models and then we turn to other models so that you get at least a little bit of a taste of everything. But there's going to be a lot more to this that if you actually need to do these analyses that you will need to go and read about on your own. So the idea that like everything that you need to know is going to come from your classes is just not accurate, even still. the ceiling for what students are expected to be able to know and do is so much higher than what it was, 15, 20 years ago, that there's no way that we could have enough classes to cover all the things. So I make a point that there's going to be extra work that you'll have to do on your own to actually be good at this. But what I hope is that I've at least given you the right search terms and maybe some articles to start with that you can look through the reference lists and examples of how people have done things so that you have at least a shot at moving down that. And the other part is that I don't know everything. So as a self-taught person, I've figured out a lot of things, but every time I teach this class, I'm hopefully going to learn a little bit more and a little bit better. So I apologize for any of the inconsistencies with respect to R across the programs or frustrations that causes with the homework. I'm doing the best I can. So that's just keeping it real. And I hope that what we're doing is useful, even if it can't possibly be as comprehensive as it should be. But you've got the rest of your lives to continue learning and developing. And I'm going to keep continuing to learn and develop. So just an aside to kind of give us some perspective about what is possible within a classroom and what is not possible to cover everything. So I'm trying to cover as much as possible, though. Okay, so any thoughts on that? Reactions? Comments? Feedback? I'm out of synonyms. Okay, fair enough. We'll move on then. So in terms of when you would need a generalized linear model, the cases that we've covered thus far are sort of the prototypical cases. Like if you have a binary outcome, it's fairly obvious that that outcome can't have normally distributed residuals and that you would probably need to do something different. The same thing is true of categorical outcomes because they're not really numbers, right? If you're predicting, whether you're in this group or that group, or whether you answered that you agree or you disagree, like those aren't numbers. So those are sort of obvious cases that would signal when you need to move past just a regular old regression model to be able to predict those types of variables as outcomes. The same thing is true of counts. It sort of is a more obvious choice because of the boundary at 0, the extra zeros, and the positive skewness. But now we're sort of headed into variables that are kind of a gray area. And there may not always be a clear decision as to what the right model should be. But I want you to have choices at your disposal that you can consider and evaluate across for different types of problems. So now we're talking about what I would call continuish outcomes. So outcomes that are numbers. They could be normally distributed, but they may not be. And we would like to think that they're continuous, that they don't have boundaries, but that is rarely going to be the case. So one example, something like proportion correct on an exam. That's a number. And because you can have, any value between, say, 0 and 1 as your proportion correct, depending on the number of items, it seems like it should be continuous. But in reality, the worst you can do is a 0 and the best you can do is a 1. So that's an outcome that has boundaries that we have to watch out for with respect to generating predicted outcomes for proportion correct. The same thing is true for scale scores. So if you have an instrument that's designed to measure, anxiety or level of preparation to do something or attitudes about some construct, those types of scale scores are also logically bounded because you can answer the minimum response to every single question or you could answer the maximum response to every single question, and those create logical boundaries. And particularly if you're dealing with a measure of some kind of trait that is undesirable, so outcomes that are problematic, like you don't want someone to have like normally distributed anxiety, right? We want people to have very low anxiety. And if you're studying traits like that are rare or otherwise that you're not going to get a normal distribution, then paying attention to these sorts of boundary issues is going to be important, even though that's not a typical use case for generalized models. So in the cases where we have these upper and lower boundaries that are created by the measurement scale, we can use a logit link to solve the problem of keeping it between 0 and 1. And any scale score that has boundaries can be transformed into a 0 and 1 scale as well, so that we can still use logit. But then the question is, what kind of distribution does it go with? We don't know. That's where we have to do a little bit of analysis to try and figure that out. There's also a bunch of continuous or continuish types of variables that are bounded in one direction at 0. So response time, for instance, collected in minutes or milliseconds, depending on your level of resolution, there is a lower bound that you can have. You can't have a response time of 0, and there's probably a boundary above that with what is physically possible. Anything that has to do with money. So the example that I just finished and put up is house prices. So that's like, what's the cheapest that you can have, the cheapest house price that you can have? I don't know, something low. I would say like $1 if maybe you're going through a messy divorce and you're going to split the proceeds and you want to like really stick it to your partner. Like you could sell your house for $1 and give them half just to make them angry. I believe that was one of the plot points in the movie, what was it? First Wives Club. That's what I'm thinking of. She sold something for $1 because they were going to split the proceeds just to piss him off. Which you can do if you're rich, right? You know, you have this kind of flexibility. What's the most a house could cost? I saw this on The Late Show recently. There was a house, I think, in California listed for $285 million. It set like a new Guinness record for houses. So no upper boundary is my point, right, for these sorts of things. In studying health and wellness, a common outcome is minutes of physical activity per day. What's the lowest amount of physical activity you can complete in a day? 0. Yeah, my watch says I have done 2 minutes of physical activity today. So at some point, me walking around my house was enough to like trigger it as to having activity, but you can't have zeros. So if you're trying to do like predicting minutes of physical activity, and particularly if you're doing it from a wearable device, right? Like if it's activity per hour or something, well, there's going to be times when people are sitting on their asses not moving. And so you're going to have like a pile of zeros in that type of variable that you'll have to deal with. There's a lot of examples like that, I think, particularly in like physical variables, not scales so much, but just things that are going to be bounded at 0 or something near 0, but then have some kind of no upper limit. So if they're not normal, then what can we do with that? And also, what do we do about outliers? So if somebody's training for a marathon and they report that they have, 5 million minutes of physical activity, that might actually be true. But that person's outcome, they may end up having like undue influence on the solution depending on their values of the predictors. So we want to watch out for that. And there are principled solutions to dealing with outliers that I want to tell you about in this unit, which is quantile regression, which is a thing that not only did I not learn that in grad school. Do you know who taught me quantile regression? This guy, my husband, upstairs, in 2012, which was the first time that we taught a class with this material together. I literally sat there and learned it with the students. But now I'm kind of mad that I didn't learn about it before, because it seems like it's super useful and not that different than regular regression, as you might imagine, since it has the same title. So we're going to do that next week. So GPA, another example of a continuish outcome with boundaries. That's a very good one, yes. It's unclear what the upper bound is in GPA. In theory, it's 4.0, but that's not actually true at this school because A+s give you overages. So I don't know what the upper bound is. At my high school, it was 4.0 because they just did everything simply, but that may not be the case anymore. So any other examples that you can think of, or things you're thinking of in your own research worlds and wondering if this applies? Now we're back to awkward silence. I taught Huey the other day what it means to have a rhetorical question. And so ever since then, he's asked me, is this a question that you want to answer to? Well, he's not sure if it was a rhetorical question. He can't remember the word, but he remembered the idea. So I'll be like, yes, this is a question I would like an answer to. I do
Lisa?
ask a lot of rhetorical questions, though, to be fair. Yes, go
Yeah,
for it.
I have a question. When we have theoretically two boundaries, for example, in GPA or maybe in scale scores, we have that there is a minimum value and a maximum value, but it is necessary that in the observed data, do we have to have values in the boundaries? For example, the minimum value and the maximum value, or do we have to have those values in the data? That's my question.
Okay, let me rephrase your question and see if I'm following.
Yeah,
Do we have to worry about this even if we haven't observed the minimum and maximum?
exactly. Yeah.
Yes, I would say, like, theoretically, yes. But if you're looking at predictions of your model and they're nowhere near outside the boundaries, then it may not be enough of a problem that it warrants a different approach. So that would one of the
Okay.
things that you can look at after you're done fitting your model is to ask your software to generate a column of predicted outcomes and see what they are and see if anything goes out of bounds, because that would be an indication that that the model needs to change to adjust for that. You might need to pick up a link function, for instance. Yes. All right. So, too legit to quit continued in predicting proportions. So we're going to use our friend Logit back again to predict things like proportion correct that have the upper and lower boundaries. And by the way, here's a formula by which you can take any scale and convert it to between 0 and 1 so that you can use these same models. That way, everything stays within the familiar Logit metric. So we're back at our link function being the log of the odds of the probability of a 1, and doing the inverse link right here. So this is the longer version of the formula where it's e to the predicted logit over 1 plus e to the predicted logit. Alternatively, you can put a 1 in the numerator and put a -1 inside the parentheses here, and that's the shorter version of the formula. And we're back to effect sizes via odds ratios. So if you can unlog the slopes, exponentiate them, then you can get to something that's used as an effect size. The question then is, what kind of distribution goes with this? And in the same way that Poisson was sort of the starting place for counts, but it's rarely going to be sufficient, binomial is the starting place for these types of variables, but it's rarely going to be sufficient. So to do this, we're actually going to convert the outcome in its continuous proportion correct metric back to number correct so that we can use a discrete distribution. So then the mean to be predicted would be the probability of a correct response to any trial, and then you would multiply that by the number of possible trials to get the actual mean of the data. So it's a little bit of a trick so that we can borrow some distributions that are going to be built into software. So binomial is one of them. It's less flexible in that it's a one parameter distribution, so there's no separate variance, and it does build in floor or ceiling effects, but not both. So that's what I mean by just one hump. It does include zeros and ones. So if you have somebody who gets 0 answers correct or somebody who gets all the answers correct, you can still model those possibilities with a binomial distribution. There's also something called beta, which we'll see, and it's very flexible in that it can take on a bunch of shapes, but the 4 question marks here means I have no idea how to interpret as parameters. There's an A and there's a B, and they control things and they defy logical explanation. So this is one that's very tricky to implement in practice, and it also is limited in that it is bounded by 0 and 1, so you can't use it for perfect scores or perfectly imperfect scores as well. But there is a combination of the two called beta binomial, in which the binomial's p parameter follows a beta distribution that allows you to add in over dispersion. So it's kind of like negative binomial being stretchy Poisson. Beta binomial is like stretchy binomial. So we'll see pictures of all of these things, and these are the packages that I'm going to use for these types of models. By the way, I don't know if you've noticed, but I've been updating your course webpage in the top box that has like all the course info, the bottom right corner has links to all of the different packages that I've used in the examples thus far. So all of the different procs and SAS, the routines and stata, and then the R documentation. So that way you have all of that collected in one place if you want to go and look up what all the options are for the software. So here's what binomial looks like. Here's a picture that I stole from Wikipedia as per my usual. And it is a one parameter distribution where the only parameter is p, the probability of getting a 1. So you multiply p times the number of trials, and that's the predicted mean of the distribution. So here are 3 examples at different levels of p for say a 20 item test, for instance. If p was 0.1, that would result in a predicted distribution that looks like this. So the blue line's over here. So it would be like a floor effect essentially, because on average people are getting 10% of the answers correct. 50-50 average would be the red lines here, and then a p of 0.9 would be the green lines. So this is a distribution that has the possibility of floor and ceiling effects built into it. It understands, based on the probability of getting any one trial right, how likely it is that you would get all the trials right, or none of the trials right, or something in between. And so if you have a proportion variable that has a mean of 0.5, that's a situation in which normal might be a reasonable approximation. So to speak to your question, Vladimir, about like if you had a distribution that looked like this for proportion correct, a regular regression model might not be a terrible alternative. But the further away you go from an even split, the more likely you're going to have skewness and have predicted values at a boundary that you'll have to address with the model. Okay. So then over dispersion is a problem potentially. What happens if, let me get the picture back here. What happens if there's more trials, say for the blue distribution, that are over here, where are more trials for the green distribution that go this way? So extra positive or negative skewness can create extra variance that we have to build into the model. I'm getting the dreaded low system resources. Am I still here? Okay, excellent. And everyone nodded right away, which means that you're still here too. I'm killing it. All right, over dispersion. So same thing here. There's multiple reasons that we can have over dispersion. The easiest to fix is that you're missing predictors from your model. So we would expect, for instance, extra variance if you say you need like a quadratic effect of a predictor, but you only put in linear, or if you're missing interaction terms or something. Those things can lead to there being more variance than the model predict. And it's fixable though by adding additional things to your linear predictor. Another thing that can cause overdispersion that we'll see in the second half of the class is correlated observations. So the one thing that all of the models we've talked about thus far have in common is an assumption of independent residuals. All of them. Question? Vladimir, go for it.
Yes, thank you, Lisa.
Sure.
I have a question related to the last slide, number 5.
Oh, wrong way.
Yeah.
Getting there.
Yes, 5.
5.
Please, yeah.
It goes slowly. Okay.
Yeah. In this case, what is the meaning of N trials and what is the meaning of C events?
Good question. N is the number of possible trials. So it would be like the number of items on a test. And then C is the number that you got correct.
Okay, thank you.
Sure. So in the example that I have, we're going to have 100 trials and then multiply % correct times the number of that 100 to get to the number of trials that are expected to be correct, because I actually only had a ratio to work with originally. But yeah, you have to know how many possible trials there are and how many, they call it events. But in practice, that usually means like the event is getting it right, but it doesn't have to be. So as an example, we're going to predict number correct for the first couple of models in example 4A, but then I have to switch to number incorrect because I couldn't find 1 inflation in the same way that I could find 0 inflation. But the good news is that if you predict number correct, you are also predicting number incorrect at the same time if you flip the signs of all of the logit values. Cough, cough, homework question. So if your model is predicting the 1, take your entire solution and multiply it by -1, and now it's predicting the 0 instead. So the logits are symmetric, which makes the math easy in that case. The other consequence of having these be two different values is that you can tell your analysis that some people had fewer possible trials. So not everybody has to have the same number possible in order to do these analyses. It still functionally works like a proportion that corrects for differences in the total that are allowed. Okay, other questions? No? Okay, fair enough. Where was I? Oh, here we go. Types of overdispersion, that's where we are here. And independent residuals, I was on that. So if there is clustering in your outcome that you're ignoring, that can show up as extra variance because it's actually extra covariance, which creates extra variance. So all of these models that we've looked at thus far are designed for situations where the observations are supposed to be independent. So if you have longitudinal data, you can't do this. If you have clustered data, say of students nested in classrooms or things like that, you can't do this. If you have siblings nested from the same family, you can't do this. You'll need to do something else. But the building block of all of the models that also address clustering via random effects are these same things. So it's all the same ideas, just with additional added complexity to the model for the variance that addresses the dependency due to whatever relationship you have amongst outcomes from the same unit of sampling. So we're going to borrow actually some of that idea to examine two different types of over-dispersion adjustments. One is additive and the other is multiplicative. And additive is the one that I had come across first because we can actually add in a random effect for each person that functionally soaks up whatever additional variability there is that the model doesn't account for. So this is a technique that you'll see abbreviated as observation level random effect, OLRE, in different sources. And I'll show you how to fit that in each of the packages. I came across this in the context of longitudinal models for percent correct outcomes. And so this extends to those situations as well. The multiplicative option for overdispersion, though, is the one that involves the beta binomial. And that one I have not seen extensions to for mixed effects models, although I'm sure they exist. So I'm less familiar with that one, but I had to learn it to be able to talk about this 2 years ago. So what is beta? Here's a picture that illustrates beta. Beta is a distribution that is bounded by 0 and 1. So it does not include 0 and it does not include 1. It's in between. And it has two different parameters that are both called shape parameters. And here are some curves that illustrate differences across them. So like if alpha and beta are both 0.5, for example, that creates this red line. If alpha is 2 and beta is 2, it creates the pink line. And combinations where one is higher than the other create these lines that look sort of crazy and skewed. So stare at this for about 10 seconds, and if anyone can explain to me what the hell these parameters mean, I will gladly listen. Exactly. This is the reason I have 4 question marks for how to use beta is what? And then it gets better because then you have different software packages that implement these things, such as, well, the mean of this variable is alpha over alpha plus beta, clearly. And then we have a scale parameter that is some kind of variance is what it ends up being, I think. It's used in making variance, which is alpha plus beta, and then variance is this. So I figured out, at least in SAS, how this translates a little bit, but I've still never successfully used this in practice. So this is one of the ones that exists, but it's way hard to use. We're only going to borrow a trick of saying that the binomial p parameter is distributed as beta to add over dispersion to the model. I don't think that I have the capability to fit a regression model with the beta distribution and understand what it means. This is one that I have not tackled yet in my self-taught instruction, but this is what it would look like. So then if you want to use beta, if you have zeros and ones, you would have to deal with those with separate submodels. So if you have zeros and you want to use a beta distribution, you would have to add in a predict it if it's zero submodel. If you have ones, you'd have to add in another submodel to predict a one value. And if you have both, then that would take 3 submodels. So to me, that seems not particularly practical, because if you have something like proportion correct, there's not a qualitative difference between getting 0 answers correct and getting 1 answer correct. Like, to predict the 0 being in a completely separate submodel doesn't seem very useful in practice. But if we use the beta binomial, then we kind of get the best of both worlds. So the binomial distribution has within its capability to be able to predict 0 answers correct or 100% of the answers correct. So you don't need a separate submodel. So binomial has that. Binomial only allows either a ceiling or a floor effect, but not both. So if we do beta binomial, that can stretch out the distribution so it allows for additional skewness beyond what's predicted by binomial. So this seems like it's a really good solution in the sense that it doesn't require you to adopt multiple submodels, and it doesn't require you to figure out what the hell alpha and beta are. But as different authors have described this differently, I have had a very hard time figuring out exactly what the parameters mean. So this is my disclaimer here, that this is the best that I've got for right now. 2 years from now, I might be able to do a better job, but this is the best I can do for right now. All of my efforts in this class this semester have gone towards adding R and trying to make R do all the things that the other packages do. So just as for instance, right? So there's this parameter that's like a stretchy scaling factor that I'm calling phi in SAS. It's given as 1 over phi in Stata, and it's given as the log of 1 over phi in R. So across those differences, I don't know how that translates into different actual predictions. That's the part that's a little bit shaky, but the general idea is that you're taking a binomial and you're adding extra variance as a function of the mean so that you can have, basically it adjusts for the additional skewness. That's the big picture of what this is for. So then we have the same issue with respect to extra zeros. So if you have zeros beyond what is captured by the binomial or the beta binomial, then you have 2 choices for what to do about it. You can either fit the 0 inflated versions of the models, and so this is what we talked about last time, being the one that's easier to find in software, but that makes less sense, because then you have a submodel to predict the logit of being an extra 0, and the zeros are also still part of the original binomial or beta binomial distribution. So there's 2 kinds of zeros to be predicted, and there's no way to know which kind a person has because all you know is that they're 0. The other option is to split it and say, I'm going to predict the logit of having a 0. So if you have something happen, and then how much for the continuous part of the distribution. But that one would require a 0 truncated binomial distribution, which is not one that I found in software. So that one seems, practically speaking, to be less available. I'm sure there's an R package somewhere. The only question is, could I figure out how to use it well enough to teach it? And that answer, friends, is no. So we'll look at, in the example that I have, we have a huge pile of actually ones, people who got 100%. So it's the same issue, but on the other side of the other end of the distribution. All right, so that then is where the example starts. So the rest of this is for next time. Go out. Come on, you can do it. Not that one. There we go. Okay, ready to see an example? Let me hide this. So I'm pulling up example 4a. This is another one where the data are not included because it's real data. And it's real data that I helped publish. So this is one of the very first papers that I ever had my name on. If you look through my CV, a common denominator is I'm second or third author because I did all of the analyses and wrote the results section. And when you're a grad student, that's not a bad strategy to add to your list. When I was interviewing at the University of Kansas, I met with someone in the dean's office, and this was a person who was like retiring in a few months, and so he had 0 F's left to give basically in our interview. I had that sort of sense from him. So he has my CV and he's sitting down in front of me and he's flipping through it and he's like reading off the journals I've published in, and he's like, "You're all over the place. What do you do?" And I said, "I prefer the term interdisciplinary, sir." But the answer to what do you do is I do quantitative methods and I help people use them. So as it turns out, the Journal of Speech, Language, Hearing Research is the one that I have published in most frequently. Because most of the departments that I've been a part of, so these are folks that I worked with at KU as a grad student, and then I ended up being hired as faculty there, 10 years later. A lot of them do work with children with special needs. And a lot of it has to do with speech issues, language issues, grammar issues. And so these are the kinds of data that I helped people analyze. So yeah, it is interdisciplinary, but I've learned at least a little bit about the field relative to what I would have learned otherwise. So it's kind of fun being a methodologist because then you get to be a content person in a lot of different areas that you don't just have to kind of stay in your lane. So interdisciplinary, but these are real data. And I don't have permission to share them, which is why they're not in the download packet. But the story is I am looking at the last occasion of a longitudinal sample of how grammatical understanding changes in children. And there are 2 groups in this analysis based on a combination of whether someone has intellectual disability or language-specific disability. And the person that I worked with here, Mabel Rice, is one of the leaders in an area called specific language impairment. And so this is a condition of children who otherwise present as typically developing. They don't have any intellectual disability or physical disabilities to speak of. However, they just can't get grammar right. So if you ask them questions like whether the word should be, do they get grammar right or does they get grammar right, they're not sure because both of them sound fine to them. And so it's a condition that doesn't really resolve as they get older. It sort of stays with them. And it can cause issues related to, feeling silly or having poor writing or other sorts of issues that, follow them over time. So this is a study about specific language impairment. And so I have a sample. In the sample, there are kids that have this condition, and there are also a comparison group of non-specific language impairment, meaning that they have other documented disabilities as well. So they have issues with grammar, but they have issues with other things, and so it's all sort of part and parcel of the same thing. So this was a study, I'm trying to remember exactly what this one was. I believe that this was a growth model of change from kindergarten to 4th grade in like 5 different measures of grammatical understanding, and the big difference was how do these 2 groups differ from each other in their growth trajectories. So this was one of the first forays that I did with growth models. And I picked this example because this is what the distribution looks like by the end of the study. So the outcome variable is proportion correct. And here is what it looks like by the time the kids hit 4th grade. Most of them have figured out how to answer the questions correctly, but unfortunately there are a few kids that are still struggling. So across all of the per year observations, the distribution isn't quite as skewed as this, but can you guess what kind of model I fit to analyze growth in this outcome? Anyone like to guess? Did I put a link function or a different distribution on it? I'll make it easier. What do you think? No, I didn't, because I didn't know any better. because I did this when I was in grad school, and I didn't know anything in grad school. So yeah, I fit this with just a regular old multi-level model, growth curve model, standard, disregarding the fact that that can't possibly be right. So, oops. And no, I have not gone back to see if the results are different after I've done it properly, because I honestly don't want to know. I don't want to know. But I think, if I remember correctly, I may have done a little bit of it and it was reasonably the same, and I felt like it was going to be okay. But there are lots of things that I have done that was the best I knew how to do at the time, and that I subsequently learned how to do better. So that's continuing our theme today of the course of development. But I want to show you that now what options are available to you. This is cross-sectional data, but most of these things could, in theory, be extended to be part of a longitudinal analysis as well. So the mean of this variable is 0.92. So on average, the kids are getting 92% of the trials correct by this fourth grade observation. So just looking at this distribution right here does not tell me what kind of model I need. Why is that? Why can't I just stare at this picture and figure out what kind of model I need? This picture is a histogram of the overall distribution of the outcome variable. That's what it is. When we worry about what type of distribution to use, is it the distribution of the outcome, or is it something else?
It is the distribution of the model residuals.
The residuals, exactly. So this looks like it's skewed, and I'm going to go with 1 inflated. I'm pretty sure that's a thing. I can say that because there's a pile of people who have a 1 here. But I don't know if this is going to be a problem until after I fit the effects of the predictors. Because it could be the case, for instance, that which group the kid is in explains why there are so many 1s, at least to some extent. So to start off an analysis, I always think it's helpful just to get a sense of what the data look like. What are the minimum and maximum values? Are they reasonable? And looking at a picture like this is going to point me towards a direction, but it's not going to dictate where I end up. So this is a marginal distribution. All of the assumptions that we're going to worry about are part for the conditional distribution instead, meaning after the model predictors have had their say. In longitudinal or clustered data, it's also after the random effects have had their say. So it's even more important in that case, because what happens at level 1 has, the additional variance due to sampling in it that you have to take out through the model, and then you can see what's left at level 1. So yeah, this points towards some kind of binomial over dispersion something. The fact that I have so many cases at this boundary means that I would probably have to worry about the model over predicting, having 120% correct or shit like that. So a logit is probably going to be necessary to rein it in because we have this skewness. The fact that I have so many cases that are out here indicates that probably it's not straight binomial, that there's going to be some kind of over dispersion. So the question will be, how well do the predictors reel that in, or do we still have to worry about that after the fact? Okay, so any questions about the story? The setup? Okay. Then let's get the predictors in here. Yeah, go ahead.
Yeah, thank you. My question is, when we conduct some analysis and we have some kind of hint that maybe we are making some mistake about the assumption of the models of the kind of this conditional distribution we are using, do we have, or can we compare different versions of the models using different link functions based on the likelihood ratio tests?
Using different link functions, you cannot do a likelihood ratio test because the models would have the same number of parameters.
And how can we know the difference between models?
So there's two ways that you can change the model. One is the link function, and you would need to use, assuming that you kept everything else constant, AIC and BIC, and also potentially things like R square or some kind of how good is the model at predicting the outcome broadly construed to decide amongst various link functions. To decide amongst conditional distributions, you can use likelihood ratio tests if the alternatives are nested. So like we can do Poisson versus negative binomial, or we could do negative binomial versus zero inflated negative binomial, because that's sort of like based on the same function in terms of calculating height, but with an extra parameter added. And if you take that parameter away, it simplifies down. What you can't use AIC, BIC, and likelihood ratio test for would be like a normal distribution versus a binomial. Like those likelihoods are heights being calculated with different metrics. So it doesn't make sense to compare them. And if it doesn't make sense to compare log likelihood values, then it doesn't make sense to compare AIC and BIC, because AIC and BIC are transformations that adjust for the number of parameters. There is something called a Wong Test. I have it referenced, I think, a couple slides. VUONG, it's somebody's name. And I have seen that used in this case where you're trying to figure out like which family to be in, like normal versus something else. But then I also recently came across some infighting on the internet about statisticians saying that no, you can't use it for this purpose, and a couple of papers that were looking at the original source and saying no, this person defined non-nested models as this, and so it doesn't apply in this case. So I think the jury is kind of out as to whether that's allowed. I know that test was initially given as part of some standard routines, and they took it off and they don't give it anymore. So I'm not sure that there are great answers to try and figure that out. One thing that we haven't talked about yet, which is at the end of lecture 4, is you can always just figure out a different way to get standard errors. Like you can do bootstrap standard errors. There's also robust standard errors, and there's a few different permutations of that. There's something in the packages where you can have it rescale the standard errors by some factor that it computes for you. And those may be sort of options if you're not sure what to do. Like if it doesn't meet a case that sort of is textbooked as to which family it is, you can always do something like that. Bootstrap type standard errors, because then you're not using distributional assumptions to figure out what they are. So a long answer to a short question, but there's not always a great way to decide. At the end of the day, the reason that you're going to the trouble to figure out which distribution you want is so that you get standard errors that are reasonable, so that you can get p-values that are reasonable, so that you can talk about things and not make type 1 or type 2 errors. So with that in mind, like if the story that you're trying to tell doesn't change across different versions, then I think you can feel good about reporting that story and saying, well, I picked this one for this reason, but the results are the same across versions. It's when the story changes enough that your discussion section would change. That's when I think it really is going to matter, and you may have to do more work to figure out what the best strategy is.
Thank you.
Sure. All right, other questions? Okay, so in this example, I only have 2 predictors. We're going to have which group the kids are in. So in the non-specific group is the reference, and then the SLI, specific language impairment, is the target group. I have mother's education centered at 12 years because that is a covariate that everyone says you have to have in these models in this area. One of the reasons why children might have problems with their grammar is because their parents are less educated and didn't speak to them using proper grammar, blah, 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 blah. I don't even know what the reasons are. I just know this is one variable that you have to control for. Okay, fine. And in the data set that I had access to from 2004, all I had was proportion correct. So I am going to have to reverse engineer number correct out of that so that I can predict that outcome directly. And it turns out that I needed to reverse engineer both number correct and number incorrect to fit everything. So I am adding in a constant for the number of trials being 100, and then computing number correct as the proportion times the number of trials rounded to the nearest nearest whole number in this case. So like if somebody has 0.8 as their proportion, now they have a variable that's 80 that's going to be the outcome. Will this be the case for homework? No, because you don't have a homework on this unit. I should have led with that, huh? I don't have a homework planned for Unit 4 because there were enough issues that I ran into that it was going to be a nightmare to get the results to be the same across packages. So you're just not doing a homework on this one. But will this be necessary in life? Yes. Because all of these routines are based on number of trials, number correct, number incorrect, and not based on the original proportion, even though what they're eventually going to get back to is the proportion. So then I computed incorrect and proportion incorrect as additional pieces that I'll be using in this analysis. And then stata looks pretty much the same way. These are all just gen statements to do that, and then I have code to do the histogram. And then I have the same thing in R. R is the one that's going to look a little bit different with respect to how it's specified. So in R, you need actually number correct and number incorrect. But the take-home message here is that you can analyze cases that have a different number possible because that information is stored as part of the analysis. So here's an empty model to start things off, and I'm predicting proportion correct, percent correct in this case. And let me get, I can get it all on the same screen. As usual, I am predicting an empty model first to figure out which way is up. So just to make sure that my software is returning what I think of as proportion correct, it should match the 0.92 that we had in the data as the mean of this outcome variable. So we're still in Glimix in SAS. This is different, this is different, and this is different across the three packages. So in SAS, after model, we normally put one outcome variable, and it's taking two. So number correct over number of trials is what's actually being predicted. That allows you to have different number of possible trials across participants. In Stata, we have GLM incorrect as the outcome, but then within this family option that tells it what kind of model, we have n trials here. So it serves the same purpose by acting as a denominator for the outcome to be predicted. When I started keying up these models in R, I found that VGLM is an option that has binomial in it, and it's binomial FF is the option that provides this. Sometimes in the VGLM package, if someone else already made something that's called binomial, they stick FF after it to make theirs a separate word. So as near as I can tell, it does the same thing. It just avoids overlap with existing stuff in R. And I initially put in incorrect and n trials, and I wasn't getting results that were anywhere near what was supposed to be. And so on a hunch, I just put in incorrect as the second one, and I got it right. So in R, it wants to know the number correct and the number incorrect, whereas the other packages want to know the number correct and the total. R also allows you to provide this information in a multivariate format. So you can have like separate columns for each item and have each column be a 0 or 1 and tell it to use all of those columns as your analysis vector. So the multiple responses thing allows you to do it with that type of data structure instead. I wasn't going to try to demonstrate that, so I just said false and did it the same way as the other packages. So for all of these, we're using a logit link to predict the proportion, and we're using a binomial response distribution to get us started. And this is an empty model, and so there are no predictors to worry about. And I am creating the Pearson chi-square over degrees of freedom residuals in R that are not directly provided, with the same caveat with respect to what the denominator is. In SAS, it's the sample size, which is 97 individuals, And in Stata, it's the sample size minus the number of fixed effects, which is only 1 here for just the intercept. Everything else I think you've seen at least once or twice before. So any questions on the setup for the code? All right. So then starting things off here with SAS, I've got the output from all 3 programs. The intercept that's given to me is 2.4593. That is in logits. So it's the same story here. All of the fixed intercepts, fixed slopes, and their standard errors that are given directly by the model are in logits, which means you'll have to unlogit them to get back to probability. So I wrote an estimate statement to do that in SAS, and lo and behold, the probability that corresponds to a logit of 2.45 is 0.92, which is exactly the mean of the outcome. So now I know for sure what the model is predicting. So hooray. However, this. Not hooray. Pearson chi-square over degrees of freedom of 21. What is that number supposed to be? If the distribution is a good fit.
As close as possible to 1.
It's supposed to be 1. So yeah, I have like 21 times the amount of variance I'm supposed to for this distribution. You know, no biggie. It's fine. I'm sure it's fine. But I don't have any predictors yet. So maybe it's just because I'm missing predictors, and once I put the predictors in, it'll be fine. So here is the Stata version of the output. The only difference is that the 21 value is a little bit different because it's using a different denominator for it. And it's telling you what type of model it is here. So the variance function is the probability of a 1 times 1 minus the probability of a 1 times the number of, divided by the number of trials. And the variance function, or excuse me, the link function then is the log of this proportion. So it's trying to help you out here. Interestingly, margins, when I asked for it to compute the predicted probability, it did it as number correct. So it returned 92 out of 100 as opposed to 0.92 out of 1. So that makes sense given that I told it that I have 100 trials, that the mean is 92. But just keep that in mind for your predictions that you have to move the decimal over 2 places to make it equivalent. And R, in this case, returned the same information. However, I don't know if you've seen this message before on the R output. I had to look this thing up, and it is, I'm guessing, 2 people's names who wrote a paper about this, because that's how these things go. What it boils down to is a difficulty in estimation. It tells you that one of the parameters had this, and so here's a little bit more information about that. That can happen when you get into situations where you have like an empty cell. So for instance, like in binary data, if you have a 0-1 outcome and it's predicted by a 0-1 predictor and you don't have like people in all 4, then it can't figure out what the slope should be, and it has to do some sort of correction for that. I think it's analogous in these cases when it has trouble estimating something, it throws an error. And so in this case, this logit is not close to the logit boundary because it doesn't have one, but it's close to the probability boundary of 0.92. So that shows up in a couple of the models because of, I think, the closeness to the boundary. But it otherwise matches everything that it does from the other packages. Okay, so let's see what happens if I put in my 2 predictors. So the linear predictor that we have right here then, adding in my SLI group variable and mother's education centered at 12 years. So that's the only difference in the syntax, is just these 2 predictors going in here in Stata. In Stata, you can also do the E-form thing to get odds ratios separately. And in, where'd it go? Here it is, in R, adding the predictors to the end of my formula here. And everything else looks the same. Still trying to use GLHT, but not expecting it to work, although this time it got very close. So anytime that I've used VGLM, The GLHT Wong Test results are always a little bit off, and I still don't know why. But maybe in 2 years when I teach the class again, or next year, I'll have figured it out by then. But it's closer this time, which is troubling that it's not always off by the same amount. So then we get to the output, and survey says, yeah, no. Dispersion, Pearson chi-square over degrees of freedom around 15. So better than 21, still not great. The intercept has moved even further over. So for the reference child who has non-specific language impairment and whose mother graduated high school, their proportion correct is predicted to be 0.956. So we get the same error in the R output because of that with respect to the Hawk-Donner effect thing. We're getting close to the boundaries of that. So it looks like, based on my output, that both of my, oh, nope, I'm in Stata, these two, both of my predictors are wildly significant, but I'm not to trust this yet because the distribution fit is so bad. So there is not nearly enough variance in the model as there is in the data up to this point. All right. And a chi-square of 273 out of R versus 273.58. So off very slightly, but it would still be enough to throw the homework system out of whack. By the way, though, off-topic comment, but on topic for homework. Jonathan and I won an internal grant competition for the College of Ed to actually make the homework system a real thing. So we got money to pay a programmer to make this a thing that hopefully other instructors would be able to use. So that will be exciting. And part of the plan is to generalize it across different software packages so that in theory you could tell it, I'm using R, and it would generate like your own correct results based on R, or I'm using SAS or whatever it is. So yeah, formative assessment movement. Cool. Hashtag I don't know what you're talking about, but thanks. So that work is in progress. If anyone knows some computer programmers who are looking for some work, let me know, because we have to hire somebody who has the skills to put this together. But anyway, so eventually this problem may be solved across getting different answers across different packages, but this would be just enough to make it not work. So, all right, let's see, what time is it? 1:38. The next one is fundamentally different in that it's adding a random effect. So we haven't talked about random effects in this class yet. We will talk more about it in the coming weeks. But generally speaking, a random effect is adding a term that adds additional variance to the model. So rather than estimating differences across some source of sampling as fixed effects, like for people, we don't have a variable in the model that's like the difference between person 1 and person 2 and person 1 and person 3. That would be fixed effects. Instead, we're adding a random effect that is going to act as a sponge and soak up any residual difference for misprediction for each individual case. So it kind of like soaks up all the variance and the extra variance in this case. So this is a strategy that I initially came across in the context of mixed models, and you can use it in the context of single level analyses too. So the addition to the model I have notated as U0. The 0 means intercept. The I means each person has a distinct value, but rather than estimate the U0 for each person directly, what we're instead estimating is their variance. So I can almost guarantee that you've seen this before. For those of you in the IRT class, random effects are latent variables. So this is the same thing as theta, functionally speaking. As long as the model understands its mean and variance, then you don't need to know what the individual values are in order to get the model to estimate. So we're adding in this additional random effect variance term, whose purpose is to soak up all of the extra variance that the binomial model does not yet account for. So observation level random effect is what this is called. And one of the reasons I like limits is because I don't even have to switch. I'm adding this term right here, which is the same type of statement I would use to add random effects of any kind in multi-level data. And even better, there is a built-in thing called Wong Test that does the corresponding likelihood ratio test for you as to whether you need that new random effect variance. Hooray! One of the few times SAS has something built in like that, and I don't have to write my own little routine. So there's only one source of variance in the model. So basically this question is saying, what if it were 0? Can you give me a test against that? Like, basically compare it to the previous model in which we didn't have a random effect. In Stata, it's this thing right here that does the same thing. So I'm in MEGLM, which stands for Mixed Effects GLM. That should be blue, by the way. I need to fix that. Yes, in case you didn't know, I manually color all of these things. So there's no way to copy Stata or R code directly into a Word document. So I have a hack that I use using TextPad, but I still have to go in and manually color things that are not readily recognized. So that should have been blue. I apologize. But this bar thing is how you tell it to add random effects. What the random effect is over, in this case, is ID, and intercepts are added by default. So the fact that there's nothing in here means please add an intercept. And then we have a line continuer to go down to the rest of the options, and the method of estimation that's being used here is what's known as Laplace, which is a type of maximum likelihood that avoids numeric integration in models with random effects. And as part of the output, it will do the likelihood ratio test to realize if it's needed for you. And in R, we're going to be switching to GLMER. So Elmer with the G. And that addition right there adds the random intercept. So the same bar with ID and a 1 meaning intercept. And I think that's a good place to stop. So I hope that you're able to enjoy your weekend not knowing how this turned out. But we'll find out on Tuesday, don't worry. Spoiler alert, adding a random effect is going to help. All right, any questions before we wrap things up for the day? No, have you lost your wills to live? Have I taken that away from you yet? A few of you look like that. Maybe you just need some coffee. Or a break, don't we all? Coffee and a break, maybe some wine. I don't know. I'm not sure at what point in the day I stop wanting coffee and start wanting wine, but you know, it's heading towards that time. But no, I have one more class to get through. So, anywho, let me know if you need help with your homework. Otherwise, have a great weekend, and I will see you next week. Bye, folks.